Hello, Chem 2. Here we are in the latest installment in equilibrium, looking at Chapter 12. Here's the objectives for the chapter. We're going to spend today's lesson mostly on just some application problems and showing you all the cool things you can do with equilibrium. And this will be the only video of the week. We're going to have one video application, give you guys a chance to dive deep into practicing these problems. So anyway, we're going to get right at it. You guys already know that the homework associated with this, I think the Chapter 11 exam is still out there, at least at the time of this taping. And you've got the Chapter 12 optional OWL and the required OWL, and the exam will pop up later on. Actually, probably be the first part of next week because we're going to do the last piece at the beginning of next week. So that's the layout for the land. Let's get started. So this is Chapter 12. It's called Gaseous Chemical Equilibrium, and all of our examples are going to be gaseous equilibriums, even though the same concepts can be held true for an aqueous equilibrium. So we've done 1, 2, and 3. We're going to dive into 4 pretty hardcore now. I know our last video we talked a little bit about 4 applications, and we're going to essentially this video is nothing but applications. So let's look at our first example. So example number 1, at 2,000 degrees, that's just really more than anything else to make sure these compounds stay as gases and are very active gases. The equilibrium constant for the reaction of the following is 2.4 times 10 to the third, and that is the Kp. If the initial partial pressure of nitrogen monoxide is 3.75 atmospheres, what's the equilibrium partial pressures of everything else, of everything in the end? Now, they did not mention at all nitrogen or oxygen. So like we said earlier, if they do not mention at all nitrogen or oxygen, it is okay to assume that those are 0. So I'm going to make the first real statement here. It can never, ever hurt to do 2 things when dealing with an equilibrium problem. It may sometimes feel like extra work if you find out later on you don't need it, but it's always great for keeping your thoughts together. And that is first to write an ice chart and lay out what you know. And then second, if an equilibrium constant has anything to do with it, write the equilibrium expression so you know what numbers are going to go where. So in this situation, what I'm going to do is I'm going to use an ice chart. So I'm going to start with my ice chart to saying I have 3.75 atmospheres of nitrogen monoxide and no oxygen and no nitrogen. Second thing is for the change, I have to figure out which side gets the pluses and which side gets the minuses. Well, in this case, we're going to use our context clues that we talked about earlier, that at equilibrium, all components must be present. At equilibrium, all components must be present. That means that the right-hand side is going to get the pluses, and the left-hand side is going to get the minuses, but with a small twist. Notice the coefficient for nitrogen monoxide is a 2, so it's going to be minus 2x, because for every 1 mole of nitrogen that is created, I'm going to need to remove 2 moles of oxygen, which means for every 1 atmosphere of nitrogen that is created, I'm going to have to reduce the pressure of the nitrogen monoxide by a factor of 2, a molar coefficient. Second thing is when we're doing an ice chart, the other piece that connects all together is I plus C equals E. So we're going to go ahead and add these up, 0 plus X and 0 plus X and 3.75 minus 2X. And we don't know what those numbers are, but we do know we can do algebra and express them as values. Okay. Second thing to do, I said one thing can never hurt is to do an ice chart and do what you can there to gather your thoughts and ideas. And we found here that there was no easy fix. Like some of the stuff we did last week, there was an easy fix because one of the things was given to you at equilibrium. There's nothing given to you at equilibrium here. So what are we going to do? Well, we're going to go to our equilibrium expression. So the Kp value, which they gave you, the expression is the pressure of the nitrogen to the first, pressure of the oxygen to the first, divided by the pressure of nitrogen dioxide to the second. So we have, it was given to us as 2.4 times 10 to the third was our number for our Kp, x times x, because we know that, times 3.75 minus 2x. This is starting to look really ugly. So if I FOIL it, are you still allowed to say FOIL? I say FOIL. If you FOIL the denominator, because we have 3.75 minus 2x times 3.75 minus 2x, and we FOIL that, we get this craziness at the bottom. And you can see where we're going. We're going down some serious hardcore algebra here, because now we're going to do the cross multiply. 2,400 times the denominator equals x squared. So we're going to go ahead and 2,400 times what it was in the denominator equals x squared. That was cross multiplying. We're going to now distribute the 2,400 into this. Yuck. And then, oh, this is starting to feel familiar, isn't it? We're going to move this x squared to the other side to make something equal 0. So we're going to subtract x squared from both sides. We get 9,599 x squared minus blah, blah, blah equals 0. So what are we doing, guys? What are we going to use? How are we going to solve for x? You know, you remember from Algebra 1 and how much you loved it. You're going to use the quadratic formula. Yes, quadratic formula is going to rear its ugly head in equilibrium, because sometimes you just got to use the quadratic formula because you're going to get these big ugly numbers because you're multiplying stuff. It's going to be messy. So yes, we are bringing forward the quadratic formula. So I don't know whether you had whichever teacher you had, whether you learned a song or whatever, but here's the quadratic formula: minus b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to get with the 9,599 being a, negative 36,000 being b, and positive 33,750 being c. We're going to plug those numbers into that quadratic formula, and bleh, hopefully we don't make any mistakes, and we solve and we get 2 answers. And which both case two both answers seem to be not too outrageous. We know that the answer we're shooting for has to be positive, and the main reason it has to be positive is because we have on the right-hand side of our expression, we have x as the atmospheric pressure. We can't have a negative atmospheric pressure, but they're both positive. Second check. On the left-hand side of our equation, we have 3.75 minus 2x. Well, if we take our bigger number here, and I'm going to pick up my calculator, and I take my bigger number of 3.75 minus 2 times 1.89, I get a negative number, which tells me that the correct answer in this situation is my 1.86. I can't subtract 2 times 1.89 from my original pressure and get a positive pressure. Now, sometimes, more often than not, one of these two numbers is going to be negative. You just can't have negative pressures or negative moles or negative concentrations. None of that makes sense. That's one of the driving forces behind trying to figure out which one's the right answer. So in this case, it's 1.86 is the correct answer. So we know that our x value is 1.86. So I go back to my ice chart. Oh, wait a second. Let's worry about the fun of saying there's another way to do this. Okay? Now, not to make light of this, quadratic equation works. Quadratic equation works, but there's an alternate way to do this. We have our expression, we have our numbers, and if right now we notice that what we have is x squared over 3.75 minus 2x, we can literally just take the square root of both sides. And you're saying, Mr. Ferrin, why'd you make me do all that work if I could do that? Well, I just want to show you that sometimes we are going to have to use a quadratic formula. When it's not as simple, when it's not as laid out to be simple, you may have to use a quadratic formula. And I want to remind you how to do that. But we could do the square root. So we take the square root of 2,400. And the square root of x squared over 3 minus 75 minus 2x squared is just simply x and 3.75 minus 2x. Okay, so I get 49 is equal to that number. Do my cross multiply. Solve for x. And yes, I get the same number. I get 1.86 atmospheres. And that's cool because that means I've got the right value. So that means I'm going to go back to my problem and say, well, if I know x is 1.86 and 1.86, I'm going to know that my nitrogen monoxide value is 3.75 minus 2 times 1.86, or 0.03, a really tiny number. Now, if you go ahead and punch these numbers in the calculator to see how close you get to the right K value, if I do 1.86, clear the calculator, right? 1.86 times 1.86 divided by 0.03 squared, I get a number that's not really that close. I get 3,844. Well, part of that's the issue of this one sig fig here. This one sig fig here is really messing with things a lot. So even though the number you were shooting for was 2,400, and I got 3,800, you're kind of going to have to be okay with that number as being a decent check. You weren't off by a whole order of magnitude. As a matter of fact, if you would have played around a little bit more with the sig figs and the like, if we would have taken these numbers out to be 3.7500 and done all the math that way, you would have gotten a whole lot closer. So you got to be okay if you're going to be spot checking in the end whether you get the right answer. Okay. Last part of this as far as application is we looked at our previous example and had the situation where one of the sides started off with 0. Well, what you were technically doing is you were calculating what's called the reaction quotient. And I know this is going to sound kind of weird, but a reaction quotient is taking the equilibrium expression and plugging in the numbers at any given moment in time. So if there's no products, which means the numerator has 0 products, then the Q value is going to be 0 divided by some number, and you're going to get the value of a Q being 0. If you start with all reactants, start with all products, and there's no reactants, then what you're going to happen is you're going to have your denominator be 0, and essentially you're going to approach infinity, and you're going to have a crazy, crazy large number. But if all 4 substances are present, which is going to be the problem in an example we're going to have in a second, at the beginning, to know which way this reaction is going to go, which side is going to be the pluses and the minuses is going to be a challenge. But not really, because what we're going to do is we're going to use this reaction coefficient to help us figure out which way it goes. Here's how it works. So we're going to go ahead and put the numbers into the expression and get a reaction quotient. It's just a value that is the result of putting the here and now concentrations or the here and now pressures into the equilibrium constant expression and getting a number. And then we're going to compare the numerical value of Q with the numerical value of the KEQ, the KP, the KC, whatever, and designate a direction. Now here's the rules. I'm going to show you another way to think about this in a second. If Q is less than the KEQ, then the reaction moves from left to right, which means the right side is going to get the pluses and the left side is going to get the minuses. If Q is greater than KEQ, then it's going to move from right to left, which means my products are going to get the minuses and my reactants are going to get the pluses. And if Q happens to be KEQ, then you're done. You're at equilibrium, life is good. Here's another way to remember that. It's a visual representation, numbers. So let's think of this whole numbers. We said that the number KEQ and the number Q can be anywhere from 0 to infinity. So it's a number line. And somewhere in the middle of that number line is the actual KEQ value, whether it be a KP, a KC, whatever. Well, here's the way this works. Suppose I do my calculation and Q is smaller than my KEQ. So my Q is over here somewhere. Well, you can see equilibriums have a tendency to want to go towards equilibrium. Systems want to get to equilibrium because that's that lull, that nothing really, no fuss, no muss, really calming spot in a reaction. So if Q is less than KEQ, it's going to try to move my reaction from my left to my right. Okay, I'm going to say that again. If I try to go from Q to KEQ, you actually have this movement of the reaction from left to right. Now, in a typical equilibrium, a typical reaction, left to right means I'm going to take my reactants and turn them into products, which means my products are going to go up and my reactants are going to go down. So the system goes from left to right, and is going to make the products go up and the reactants go down. And the reverse is true if my Q happens to be on the other side. If my Q is on this side, same logic. Q is greater than KEQ. Remember, the numbers on the right-hand side of a typical number line are bigger than the ones on the left-hand side. And the Q is bigger than my KEQ. Then what's going to happen is the reaction is going to go from products to reactants. My products are going to be lost and my reactants are going to be created in order to get to KEQ. It's going to go from left to right. Think in terms of the way a reaction is typically written. Reactants are on the left-hand side, products are on the right-hand side. The things that are on the right-hand side are going to be reduced as they react to make the things on the left-hand side. It shifts towards the left, and the products are going to get smaller and the reactants are going to get bigger. So ways to remember what to do. Now let's see this in action. Let's see how we use this, or how we could use this. So here we have a system, and it only consists of two pieces. It's dinitrogen tetroxide and nitrogen dioxide. And I want to know which direction this reaction will go. If I know the Kp is 11, and I know when I start, I put 0.1 moles of dinitrogen tetroxide into the material, and I put 0.2 moles of nitrogen dioxide in a 2-liter container. And again, another important part here is it's all happening at 100 degrees Celsius. What's going to happen? Which way is this going to go? That's all I want to know. I don't want to know what the concentrations are at the end. I want to know which way it's going to go. So let's look at it. I have my reaction. I have my Kp. I know what it is. It's number 11. I know it's at 100 degrees. I know my initial number of moles. I know my initial volume. It sounds like since this is a Kp, I need to get pressure. So I need to figure out what R value to use. And then I have to figure out what the reaction direction is. So the strategy that I would use is I'm going to calculate the partial pressures of everything, put them into the expression and find out what the Q is, and then compare my Q to my KEQ to figure out which direction it's going to go. So my pressure, PV equals nRT, which can be converted to P equals nRT over V. See what I did? I just divided both sides by V. And I plugged the numbers in for dinitrogen tetroxide. And then I do the exact same thing for the pressure of nitrogen dioxide, and I get 3.1. So I have my values. I have my pressure of dinitrogen tetroxide and my pressure of nitrogen dioxide, and put them both together. There's my values. First things first, get the partial pressures. I see what I use. I use my 100 degrees Celsius, which is 375 K. It was a 2-liter container. I use a 0.8206 R value. Pretty straightforward. Then what I'm going to do is I'm going to put these two values that I got for pressures into my equilibrium expression. So it's nitrogen dioxide squared over dinitrogen tetroxide to the first. Put the numbers in, I get 6.4. Now, I need to compare. I know that 6.4 is less than 11. My Q is less than my KEQ. My Q is less than my KEQ. So I know that I have to proceed from left to right. So as a result of this reaction, if I had to put my pluses and minuses in, my pluses would be on the right-hand side and my minuses would be on the left-hand side. Okay, let's see it work. Ready? So they talk about as written. That's kind of an important piece. When we talk about left to right, I keep going back to saying that a typical reaction shows reactions and products. We know that we're in a unique situation here in that equilibriums have both directions going at the same time. So in a weird sense, everything's a reactant and everything's a product. But when we're talking about reactants and products and left to right, it's always as the expression is written, because also recognize that the expression that you write, as the expression you write, the KEQ expression you write, is based on how the equation is written, what's on the right-hand side and what's on the left-hand side. Okay, so let's try one. So at a certain temperature, Kp is 0.44. And I'm going to go ahead and take 2 moles of iodine trichloride, which is a solid, and it's going to decompose into chlorine and iodine gases. So I'm initially going to start with none of the chlorine and iodine. I'm just going to put 2 moles of iodine trichloride solid into a container and let it do its thing. Well, because the coefficients are 1 and 3, I know that my chlorine is going to, in the end, produce 3 times as many moles of chlorine as it does iodine. I'm going to produce 3 times as many moles of chlorine as there are iodine, and that's because of stoichiometric relationship. With that being said, pretty simple jump to the end of the story. What's the partial pressure of everything at equilibrium? Okay, let's look at it. So I know that I have my equation. I know because iodine trichloride is a solid, I don't have anything in the denominator. I have Pi to the first, P chlorine to the third. I don't have anything in the denominator. It's the equivalent of saying it's over 1. I don't have anything in the denominator because the reactants are all solids. I'm going to go ahead and think in terms of X and 3X because it said, or we know from the statement, and we should know from stoichiometrically, that iodine is going to be X, some value we're shooting for, but chlorine is going to be 3 times that. So I just call it X and 3X. I'm going to plug those numbers into the Kp expression, or those variables. So Kp equals X to the first, 3X to the third, and do the math. I get 27X to the fourth. Don't get tricked into 3 to the third power. That's going to be 9. No, 3 to the second power is 9. 3 to the third power is 27. So I find out that I have Kp, whatever my Kp value was given to me, is going to be 27 times X to the fourth. The Kp value that was given to you is 0.44. So now that time to do a little bit of algebra. X to the fourth is equal to 0.44 divided by 27, or X is equal to 0.44 divided by 27 raised to the fourth power. I left it in my calculator because of the whole sig fig thing, so I just left it in the calculator, punched in 0.44 divided by 27, then I raised it to the, actually I raised mine because I didn't have a fourth button. I raised it to the 1/4 power. That's the same as taking something to the fourth root. And then I get that my pressure, X, is 0.357. So what does that mean? That means my iodine pressure was 0.357 and my chlorine pressure was 1.07. Now, one of the great things about equilibrium is you can, like I saw in the previous example, when it's numerical stuff, you can check your answers and see if you're close. Make sure you're kind of reasonably close. So what I did just here was I went ahead and punched these numbers into the expression and wanted to see what number I get. Well, guess what? To 3 sig figs, I get 0.440. That tells me that these two pressures do match the equilibrium expression value. Again, you have to be okay with being a little bit off because that will happen, but this just tells me that I've got the same answer. I'm good. Okay, you can always check your answers. That was kind of cool. Everything links together. Okay, last example. Okay, and this one's actually going to use the K, which way gets the P. Okay, so which way gets a plus and which way gets a minus, resulting on the Kp. I've got a reaction where I've got the reaction above, sulfur dioxide and nitrogen dioxide in equilibrium with nitrogen monoxide and sulfur trioxide, and everything's a gas. And everything as a gas, initially I put all of my components at 2.26 atmospheres. I intentionally make everything 2.26 atmospheres to start off with. And then I allow it to do its thing. I want to know what's the partial pressures of every one of the gases at equilibrium. Okay, so first thing we need to do is compare the total pressures initially with the total pressure at equilibrium. You should think about that one. We'll talk about what happens there. Okay, hopefully I'll remember to do that. So I start with my ice chart. 2.26, 2.26, 2.26, 2.26. Which side gets the plus, which side gets the minus? Which side gets the plus, which side gets the minus? Well, we have to do that. We have to calculate our Kp and our Kc. There's our Kp expression. They said the Kp value was 84.7. We put all of our numbers that we start with in our expression, and we get that our Q is 1. So since our Q is less than our Kp, our Q is less than our Kp, it's going to shift from left to right, which means the left side is going to get the minuses and the right side is going to get the pluses. Left side is going to get the minuses, right side is going to get the pluses. And then the almighty I plus C equals E, add the top and the bottom together. And we get the algebraic equivalent of what the pressures are going to be for all 4 components. We're going to put them into the Kp expression now. And then, again, since we have this fancy, we recognize that the top is a square and the bottom is a square, we're just going to take the square root of both sides and make life a lot easier. So we get the square root of both sides being 2.26 plus x over 2.26 minus x equals 9.20. That's the square root of 84.7. Do my cross multiply and then solve for x. and I get that my pressure, my X value, the number that I'm going to remove or add to 2.26 is going to be 1.82. So my nitrogen monoxide and my sulfur trioxide, which are the right-hand side, I'm going to have to add 1.82 to the pressure, and to the pressure of the sulfur dioxide and the nitrogen dioxide, I'm going to subtract 1.82. Now, the last part of the question is, so what's the total? How does the total pressure compare? Well, we started off with the total pressure. I'm going to do this on my calculator real fast. We started off with total pressure of 2.26 times 4, or the number that I get is 9.04 atmospheres, total pressure. Well, let's do this. 4.08 plus 4.08 plus 0.44 plus 0.44. I get the same thing, 9.4. Well, that kind of makes sense. Notice I have a no change in my number of moles overall. I start with 2 moles on the left, I end with 2 moles on the right. So how much the pressure decreases on the left-hand side, the pressure on the right-hand side is going to increase. Now, with that being said, I want to say one more thing. This idea of pressure on either side increasing or decreasing. All these compounds are in the same container. So there's no right side of the compound and left side of the compound. When we say the right side of the equation, left side of the equation, we're talking about the compounds that are on the left side, compounds that are on the left side, or compounds that are on the right side. We make sure we identify them relative to the equation, but they are not on the right side of the container or the left side of the container. They're all mixed together and they all work in tandem. Okay, so that's the end of today's lesson. Actually, it's the end of this week's lessons. Just want to do one PowerPoint that did a handful of practices and give you ample opportunities this week to dive deep into the OWL problems more than anything else, because you're going to have to practice a lot, and there's a lot there that's associated with doing equilibrium style problems. But what's next? What we're going to do next is the end of this chapter, and we're going to focus on what happens when you stress out the system. If the system is at equilibrium and you introduce some type of a stress, what's going to happen to that system? So anyway, hopefully you guys are all safe, healthy, practicing your social distancing, and going to try to take advantage of what is turning into a bit of a spring fling of weather. I'm very saddened by the fact that I will not be able to see your smiling faces at all for the rest of the year, but hopefully I'll see a lot of you guys in AP Chem either next year or the following year. You guys have a fantastic day, and until next time, always remember, never forget, sig figs do matter. Toodles.